Hi, my name is Matthew Runyon, and this is an intelligent system to analyze sketch solutions to open-ended truss problems. So first, we'll start with the problem. So engineering students need practice with open-ended problems in order to improve their critical thinking skills and help prepare them for jobs. But open-ended problems can be difficult to grade and also time-consuming. So instructors typically must validate each student's calculations, and every student will have a different solution to the problem. And so basically large classes can make open-ended problems infeasible for instructors to assign. So for this project, we looked at an open-ended problem for a statics class, which was designing a 2D truss bridge. So some existing systems and their limitations. There's some statics homework systems such as Wiley Plus or McGraw-Hill Connect, but these systems don't require free body diagrams, and they typically don't have open-ended problems. All the problems just have a single solution and are what you would normally find in a textbook. And then there's also truss analysis systems, which would be systems that an instructor might use to grade an open-ended truss problem. But this still requires a lot of time for the instructor potentially, and could have a steep learning curve in order for the instructor to use something like SolidWorks simulation just to check their students' answers. So the solution, of course, is to use AI. So we wanted students to be able to draw the truss by hand. And so we used sketch recognition in order to understand the truss and also in order to help check the solution against open-ended constraints. So the students receive immediate feedback with automatic grading, which helps reduce the burden on instructors so that they don't have to grade these problems by hand. And so we created a web app which automatically grades open-ended bridge design problems. So a quick system overview. The students first draw the truss they design. When they're done drawing the truss, they click a finished button. This just prevents the system from providing visual feedback and recognizing a truss that's an intermediate step to the truss that they wanted to draw ultimately. The students then draw the forces that are applied and input side lengths and angles. So if the students provide enough side lengths or angles to define one of the triangles in this case, then the remaining side lengths and angles are automatically filled in for them. And then the students provide the max load that the truss can support, and the system automatically grades it and provides them with feedback. So we'll cover the truss recognition first. So the first step is to segment the strokes, and we use an algorithm called short straw to create different substrokes from what the student drew. And on top of that, we also segment the substrokes such that every substroke intersects another substroke at its endpoint only. So you can't, if you have a system like this where you have a T, you'd end up with 3 separate substrokes, even if it was drawn with 2 strokes. Then we convert the substrokes into a graph. So if the endpoints of the substrokes are within 40 pixels of each other, we determine these to be intersecting at the same node in the graph, and then so we combine them and call them the same node. And then we check if the graph is connected. So the problem is to create a single truss. So if there's any disjoint section, then it's not a single truss. It would be multiple trusses or just a random shape. And then we check a couple of simplifications for the introductory class. So we require the students to make their trusses completely out of triangles. It is possible to have trusses with other shapes within them, but triangles are the most common and most typically what you would see in these classes. And then we also check that the triangles share an edge with another triangle. And this is part of a static determinacy check, which we'll also talk about in a moment. So then after the truss is recognized, we find the logical coordinates of the truss. So the logical coordinates are what we refer to as the actual position that the student intended based on their labels and not based on what they drew, because it's very, very unlikely that anyone would draw perfectly to scale of what they wanted. So we start by looking at node A, we call that point 0, 0, and then we find the nearest node to the horizontal axis from A. So in this case, it's F, and it's close enough to the horizontal axis that we don't ask the student for an angle. If it were further away from the horizontal axis at an angle, we would then require the student to input the angle in between the horizontal axis and that beam. So using the student's input, we can say that F is at position 4, 0. And then we do a breadth first search from A in order to find the remaining coordinates. of the unknown nodes. So we would go to C and see, since we know the coordinates of A and F, we can calculate the coordinates of C using a rotation matrix. So that's this matrix here. And what we do is we find the unit vector from point A to point C using the rotation matrix. And then using the coordinates of A plus the input from the student, we can determine the coordinates of C using this equation. So the next step is once the student submits their answer, we check the internal forces. So first we check for static determinancy. This is an equation based on the number of nodes, beams, and external reaction forces in the truss. And then we generate, if it's statically determinate, we generate two equations of equilibrium per node, one in the x direction and one in the y direction. And so these equations will be in the form of ax plus b equals 0. So in this case, we would have up to 6 equations, but we remove the equations that deal with the external reaction forces because we don't need them. So we have this coefficient matrix, which is the component force of each beam reaction force. So we have beams AB, AC, and BC. And then we have the externally applied forces, which in this case is P. And so we can use the logical coordinates to determine these components of the beam forces. So then we check the constraints. So we use LU decomposition in order to solve the system of equations from before. So we assign a value of 1 for each possible external force. So in this case, we only have one value P, but this can be scaled up. If you have P and Q, for example, you would solve the same system of equations twice, once with P equal to 1 and Q equal to 0, and then once with those values reversed. So in that case, you use superposition to combine the multiple external forces. So this right here gives the effect of the load P on the internal force in each of the 3 members. So then we can check that the constraints are met, which in this case, there is a minimum and maximum length for the bridge. And then there was amount of tension and compression that each of the beams could support. And then there was a minimum load that the bridge needed to support. So just a quick evaluation of the interface. We tested this in an introductory statics course. There were 58 students that participated between software and paper and pencil groups. And of those 58, we took 16 students for focus groups, and we analyzed the focus groups using conventional content analysis. And as a note, the problem was assigned just before COVID caused classes to go completely virtual in March of 2020. So the student experiences with the problem, overall, the students seemed to like the problem. They liked that it was different. They felt it was helpful. But we noted that the students in the software group mentioned that they felt that they applied iterative design more and that the problem was helpful and encouraged their creativity and critical thinking more than the paper and pencil group mentioned. We think that this was due to the fact that the students in the software group had immediate feedback, whereas students in the paper and pencil group didn't receive any feedback until they submitted the problem. The student experiences with the software overall, most of the students in the software group mentioned that they liked the real-time feedback and they found this system efficient to use. Some dislikes were that they felt it was a little bit messier, which we think was probably due to students, not every student having a stylus to use and instead having to use either a mouse or use their finger on a tablet. And then there were a couple of notes about intermittent recognition issues from some of the students. So with that complaint in mind, we investigated what caused some of those issues. And so we looked at any time when a student had to erase a part of their sketch as a potential spot for where an error may have occurred. And of those, there were only about 9 potential spots. So looking through them and watching playbacks, most of the errors were due to user error, where they were either drawing things out of order or not drawing a complete truss and thinking that it should have been recognized as a truss. There was one instance where a student drew a beam with multiple strokes like this, and that wasn't supported, and so that was a recognition problem that we need to address. And then there were a couple of instances of what we call short and fat arrows, where we just needed to relax some of the constraints for our error recognition system. Talking about the algorithmic accuracy, overall, we tested the truss on a set of 3,000 trusses and non-trusses. It correctly rejected all of the non-trusses, and it missed a handful of real trusses, mostly due to them either containing non-triangle shapes or having multiple strokes for a single beam. and we got an F-score of 0.997 on our data set. So in conclusion, students felt the problem was valuable practice. Most of the students reported positive experiences with the software, and then the students attempted more designs and were more successful in general with this problem on software over paper and pencil. There's more info about this in a paper that we had published in FIE. And then some future work, we want to expand the types of trusses that can be accepted and also add analysis for statically indeterminate trusses. So thank you for watching.